All right, in this video, we're going to talk about section 3.5 dealing with implicit differentiation. And in this video, we're going to use implicit differentiation to find derivatives. And then we're going to find the equation of the tangent line to the graph of an implicitly defined function. And then we're going to solve applications involving implicit differentiation. All right. Up until now, you were taking derivatives of functions that were in the explicit form. Okay, so like in this equation of the curve, it was in the form y equal x squared minus 5x, or f of x equal to x squared minus 5x. For example, it's just only example. And what you're seeing here is the explicit form, where y is given as a function of x. However, graphs can also be specified by equations of the form f of x comma y equal to 0, such as this one. F of x comma y is equal to x squared plus 4xy minus 3y squared plus 7. We call that the implicit form. So with the implicit form, you may or may not be able to solve that equation for y. Okay, so if we were to consider the equation y equal x squared minus 5x, we can compute the equation of the tangent line by using the derivative of y prime being equal to 2x minus 5. We call that explicit differentiation. Now that equation, that original equation, can be written like this: f of x comma y is equal to x squared minus 5x minus y equaling to 0. And we can calculate the derivative of y from that. Now, this is what we call implicit differentiation. And that's the basis of this entire section 3.5 is going to be on implicit differentiation. So what we want to do here in this section is to find a single expression for the derivative directly from an equation f of x comma y equals 0 without first solving for y. This technique, called implicit differentiation, is demonstrated through examples. Now, to understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x. This means that when you differentiate terms involving x alone, you can differentiate as usual. However, when you differentiate terms involving y, you must apply the chain rule. Yeah, we talked about that in the last video. And this is because you're assuming that y is defined implicitly as a differentiable function of x. Okay, that's very important. Okay, anytime you differentiate terms in y, you have to apply the chain rule. Now, on the next page is some guidelines for implicit differentiation. And that's this. Number one, you're going to differentiate both sides of the equation with respect to x. Then you're going to collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. Then you're going to factor dy dx out of the left side of the equation and then solve for dy dx. Okay. So we're going to apply those guidelines to a few of these examples that I have here in this video. So starting with example 1, we're going to use implicit differentiation to find dy, well, define y prime, I should say. And then evaluate y prime at the ordered pair 2, 3. And here we got 4x cubed minus y cubed minus 5 equal to 0. And here we're going to use implicit differentiation to find the derivative and then evaluate the derivative at the point 2, 3. So the idea here is this. We're going to take the derivative of each and every single term with respect to x on the left side and on the right side of this equation. So that's why you see the derivative with respect to x of each and every term on the left and on the right side. So on the left side, if I take the derivative of 4x cubed, here I bring the power down, multiply by 4, you're going to get 12. Copy that x over to the one less power. So it'll be 12x squared. And then minus the derivative of y cubed. I'm going to bring the exponent down, bring the 3 down, copy the y over to the one less power, that'll be squared. But here I'm taking the derivative of something that has a y in it. So I must include dy dx, because I'm assuming that y is some differentiable function of x. So every time you take a derivative of y, you must include dy dx. The derivative of minus 5 will be 0. And then that's equal to the derivative of 0. Again, that's 0, because the derivative of a constant is 0. Now here you want to collect all the terms involving dy dx on the left side of the equation and move all the other terms to the right side of the equation. Now I only have a dy dx right here. I need to move the 12x squared over to where that 0 is. And I'm going to do that by subtracting 12x squared on both sides. So when I do that, I have negative 3y squared dy dx equaling to negative 12x squared. And then to solve for dy dx, I'll divide both sides by negative 3y squared, because I want to get dy dx by itself. So that means dy dx will be equal to, let's see, negative divided by negative, negative will be positive, so 12 divided by 3 will be 4, and then x squared in the numerator, and I'll just have the y squared in the denominator. So this is what dy dx is going to be, or y prime if you want to call it that, 4x squared divided by y squared. Now we're going to evaluate y prime at the ordered pair 2, 3. So no, y prime is going to be 4x squared over y squared. Now keep in mind the y prime and dy dx are just, they're the same thing. There's just notations of taking the derivative. So at the ordered pair 2, 3, and in this case your x is 2 and y is 3, then y prime would be this. I substitute the x with 4 and the y with 3, so it'll be 4 times x, which is 2, and that's squared, divided by y, which is 3, and that will be squared. Let's see, if I square the 2, that's going to be 4. Square the 3 is going to be 9. And 4 times 4 will be 16 over 9. So that means that y prime at the ordered pair 2, 3 would be 16 ninths. Okay. So here's dy dx will be 4x squared over y squared, and y prime at the point 2, 3 will be 16 ninths. Okay. All right, here's another example of this. You want to use implicit differentiation to find y prime for the equation below and evaluate y prime at the indicated point. So here we got y squared plus 3y plus 6x equal to 0. And the point we're dealing with is negative 3, 3. So in this case here, we're going to take the derivative, just like we did in the last example, of each and every term on the left side and on the right side. Now, me personally, I like to use this notation, the derivative with respect to x. That way you can see that I'm going to be taking the derivative of each and every term in that equation. All right, so for y squared, the derivative of that, bring the 2 down, copy the y over to the one less power, so it'll be 2y. But since I'm taking the derivative of y, I must include dy dy dx. Because again, I'm assuming that y is going to be some differentiable function in terms of x, plus the derivative of 3y would just be 3. Again, I'm taking the derivative of y, so I need to include dy dx. Now, plus the derivative of 6x. I'm taking the derivative of 6x with respect to x, so that derivative would just be 6, and that's equal to the derivative of 0. Of course, that will be 0. All right, so here I'm going to collect all the terms, have dy dx, and then move all the other terms to the other side. I have dy dx. These two terms I'll leave on the left side. I'll move the 6 over to the right side by subtracting 6 on both sides. So here I'm going to have 2y dy dx plus 3 dy dx equal -6. Now notice I can go ahead and factor out the dy dx on the left side. So here they both have dy dx. Both terms have dy dx in it. I can factor that out. Now I'll be left with just a 2y plus 3. That's equal to -6. And now I can get dy dx by dividing both sides of this equation by 2y plus 3. So dy dx then would be equal to -6 over 2y plus 3. Or I can say this, since they want us to find y prime, I can say y prime is -6 over 2y plus 3. Now, at the point -3, 3, that means x is -1, and I mean -3, and y is going to be equal to 3. Substitute in that equation. So here, y prime then would be equal to -6 over 2 times, your y is going to be 3, so it'll be 2 times 3 plus 3. So here, y prime would be -6 over 2 times 3 is 6 plus 3 would be 9. And I can reduce -6/9 to -2/3. So that means that y prime would be -2/3 at the point -3, 3. And of course, dy dx, or y prime, would be -6 over 2y plus 3. Okay. All right, here's another example. Say here's something like this: x plus y, xy plus 12 equal to 0. And we're going to use implicit differentiation to find y prime, and then evaluate y prime at the point -3, 4. So in this case here, x times y. That tells me I need to use the product rule here, because I got a product of x and y, so I need to apply the product rule to take its derivative here. Okay. So again, here I just take the derivative of each side of the equation. Okay. Now the derivative of this, x times y, using the product rule would be this: the first, which would be your x, times the derivative of the second. The derivative of y will be 1, but I must include dy dx since I'm taking the derivative of y, and then plus the second, which is your y, times the derivative of x, which is 1. And the derivative of a constant, here the derivative of 12 will be 0, because the derivative of a constant is 0, and this will be equal to 0. Now, if I simplify this, I just have x times dy dx plus y is equal to 0. and I need to get dy dx by itself. So I need to subtract y on both sides. That means x times dy dx will be equal to negative y. And just get dy dx by itself, I'll divide both sides by x. That means dy dx is equal to negative y over x. Or I can say y prime would be equal to negative y over x. So now, let's evaluate y prime at the point negative 3, 4. That would mean y prime would be equal to, here x is negative 3 and y is going to be equal to 4. So bring over the negative sign here, your y is going to be 4 over x, which is negative 3. And negative divided by negative will be positive, so y prime will just be 4/3. That's all there is to it. Okay. So your derivative, y prime, will be negative y over x, and at the point negative 3, 4, y prime will be positive 4/3. Okay. All right, let's look at this next example. Here we're going to use implicit differentiation to find y prime and evaluate y prime for the equation x squared y minus 3x squared minus 4 equals 0 at the point 2, 4. All right, so let me go ahead and write the equation down. X squared y minus 3x squared minus 4 equal to 0. So here we're going to use implicit differentiation by taking the derivative of each and every term on each side of this equation with respect to x. All right, so now for the derivative of x squared y, this is x squared times y. I'm taking its derivative. That means I need to apply the product rule. And that product rule will be this, the first term, which is your x squared, times the derivative of y will be 1 times dy dx. Again, I'm taking the derivative of y, so I must include dy dx. Plus the second times the derivative of the first, the derivative of x squared, that's 2x. So for this term, I had to apply the product rule. For the minus 3x squared, I can take its derivative by just using the power rule. By doing this, putting the minus sign down, bring the 2 down, multiply by 3. 3 times 2 will be 6. Copy the x over to the 1 less power, so it'll just be 6x. The derivative of a constant is 0, so the derivative of minus 4 will be 0, equaling to the derivative of 0. Again, that will be 0, since the derivative of a constant is 0. All right, now if I clean this up just a little bit, I'm going to have x squared dy dx plus y times 2x would just be 2xy minus 6x is equal to 0. And then I'm going to get dy dx by itself. I'm going to move the 2xy and the minus 6x over to the other side. So to move the 2xy over, I'll subtract 2xy on both sides. And to move the minus 6x over, I'll add 6x to both sides. So I'm doing all of this in one step. So now I'll have x squared dy dx that's equal to negative 2xy plus 6x. And if I divide both sides by x squared, so I can get that dy dx by itself, that will mean dy dx is equal to negative 2xy plus 6x. All that's divided by x squared. And here's what I can do here. I can factor out the x in the numerator. Because notice in negative 2xy and plus 6x, there's a common factor, which is your x. I can factor out the x. When I do that, negative 2xy divided by x will be negative 2y, plus 6x divided by x will just be 6. All that will be over x squared. And in this case here, I can divide out an x in the numerator and an x in the denominator with my x squared, because x squared has x in it. I'll be left with an x. So one of the x's divides out with the x in the numerator, leaving me with x in the denominator. So this will be, and I can write this as either negative 2y plus 6 divided by x, or 6 minus 2y divided by x. All right, and now let's find out what y prime is at the point 2, 4. So y prime is that 6 minus 2y over x, and we're going to evaluate that at the point 2, 4. So y prime then will be equal to 6 minus 2 times your y is going to be 4 divided by x, which is 2. Again, this is x and that's y. Now simplify this. This will be y prime is equal to 6 minus 2 times 4, which is 8, all over 2. 6 minus 8 would be negative 2. Negative 2 divided by 2 would be negative 1. So the value of y prime at the point 2, 4 would be negative 1. When y prime would be 6 minus 2y divided by x. All right, here's another example. Let's say I want to use implicit differentiation to find y prime and then evaluate y prime at negative 3, 0. Now here we got 9e to the y equaling to x squared plus y to the 4th. So now we got an exponential function involved here. So what I need to do here is just take the derivative of each side, of each and every term of each side of this equation. All right, now, for the derivative of 9e to the y, I can bring the 9 down and take the derivative of e to the y, which is the easiest derivative to take. That would be e to the y. But notice I got the y up here, so I need to include dy dx when I take the derivative of y. Okay, here I'm applying the chain rule. Is equal to the derivative with respect to x of x squared, that's 2x, plus the derivative of y to the 4th with respect to x, that will be bring down the 4, copy the y over to the 1 less power. But since I'm assuming that y is going to be some differentiable function of x in terms of x, I need to include dy dx. Now I need to collect all the terms that have dy dx on the left side, and all the other terms will be on the right side. So I need to move the 4y cubed dy dx over to this side by subtracting 4y cubed dy dx. So on the left side, I'm just going to rewrite this as 9e to the y dy dx minus 4y cubed dy dx. That's equal to 2x. And from this, I have dy dx on both terms here. I can factor out the dy dx. So that means I'm going to have just 9e to the y minus 4y cubed equaling to 2x. And then divide both sides by 9e to the y minus 4y cubed I'll divide that on both sides. So I'm left with dy dx equaling to 2x divided by 9e to the y minus 4y cubed. So that's what dy dx is going to be. 2x divided by 9e to the y minus 4y cubed. And I'll write that as y prime up here. 2x over 9e to the y minus 4y cubed. Now let's find out what that y prime will be at the point -3, 0. So again, x is -3 and y is 0. We just substitute those values into y prime. So that means y prime at -3, 0 will be this. 2 times y 0 divided by 9e to the y, that's 0, minus 4 times, hold on. Sorry, x is -3, so this should be 2 times -3 in the numerator. Two times -3. 9e to the y, that's 0, and then 4 times y, which is 0, and that's going to be cubed. Okay? So that means 2 times -3 will be -6. E to the 0 is 1 times the 9 would be 9. Minus 0 cubed is 0 times the 4 in front would be 0. So now we're going to be left with y prime equaling to -6 over 9 times 0, which is 9. And I can reduce -6/9 to -2/3. So y prime ends up being -2/3. All right. So y prime will be -2/3 when y prime was equal to 2x divided by 9e to the y minus 4y cubed. Okay. All right, look at example 6. In example 6, you got this. You want to use implicit differentiation to find y prime and then evaluate y prime at the point 3,1. This time we got x squared minus 9y squared is equal to the natural log of y. All right, so we're going to use implicit differentiation by taking the derivative of the left side and the right side with respect to x. All right. So now the derivative with respect to x of x squared, that's simply going to be 2x minus the derivative with respect to x of minus 9y squared. If I bring the 2 down, multiply by 9, it'll be minus 18 here. Copy the y over to the 1 less power, but I'm taking the derivative of y. That means I need dy dx. Then that's equal to the derivative of ln of y. That's one of the derivatives of a natural log function. That's just going to be 1 over the y. But again, since y is a function of x, I need to include dy dx. All right, now notice I got the y in the denominator. Let me get rid of that y that's in that denominator by multiplying both sides of the equation by y. I'm using different colors so I can show you what I'm going to do here. In fact, let me make this simpler by multiplying each and every term in the equation by y. And then I'll have y times this right here, 1 over y dy dx. You're going to see y. If I multiply y times the 2x, I have 2xy minus 18y times the y will be 18y squared, and then dy dx equals y times 1 over y. The y's divide out. All I'll be left with is 1 dy dx, or just dy dx. Because I'm getting rid of the fractions here in the denominator, so that way I have a equation that I can easily get dy dx by itself. Okay. Normally you'll put all the terms that have dy dx on the left side. However, it'd be easier to move the minus 18y dy dx over to the other side by adding 18y squared dy dx. Probably be easier to do it that way because I don't want to deal with a lot of negative signs. The left side would be 2xy. The right side, I have dy dx plus 18y squared dy dx. Now, if I factor out the dy dx on both sides, on the right side, dy dx divided by itself will be 1, plus 18y squared dy dx divided by dy dx will be 18y squared. So I have 2xy is equal to dy dx times the quantity 1 plus 18y squared. And I'll go ahead and divide both sides of this equation by 1 plus 18y squared. Okay, and I'm going to continue this up here. So that means here that 2xy over 1 plus 18y squared will be equal to dy dx. Because this is gone, I'll be left with dy dx. Or we can just say that y prime is going to be equal to 2xy over 1 plus 18y squared. Now at the point 3, 1, we want to find out what y prime is at the ordered pair 3, 1. Okay, so what we need to do here is just substitute the x with 3 and the y with 1. So y prime would be 2 times 3 times 1 all over 1 plus 18 times y, which is 1, and that's going to be squared. So here y prime is this 2 times 3 is 6 times 1 will be 6, divided by 1 plus 1 squared will be 1 times the 18 will be 18, and then 1 plus 18 will be 19. So y prime ends up being 6 over 19. So that is what y prime would be at the point 3, 1. When we found out that y prime is equal to 2xy divided by 1 plus 18y squared. Okay. All right, let's look at problem number 7. Example 7, I should say. Let's say I want to find the equation of the tangent line or tangent lines at the point or points on the graph of the equation y squared is equal to, y squared minus xy plus 10 equals 0, where x is equal to 7. So in this case, our equation is y squared minus xy plus 10 is equal to 0. Minus xy. Plus 10 is equal to 0. And we have here that x is equal to 7. Since x is equal to 7, we can just substitute each x in this equation with 7. So we got y squared minus x, which is 7, y plus 10 equal to 0. Now here we got a quadratic equation that we can factor into two binomials here. So that means y squared minus 7y plus 10. I'll factor that into two binomials here. So break up the y squared as y and y. The middle term is a minus and the last term is a plus. That means both factors have to be minus. And I need factors of 10 that will give me negative 7x. Negative 7y is a middle term. So minus 5 and minus 2 would work. So I have y minus 5 times y minus 2 is equal to 0. Then we set each binomial factor equal to 0. So that means y minus 5 is equal to 0, or y minus 2 is equal to 0. And if y minus 5 equals 0, that means y is equal to 5. Or for y minus 2 is equal to 0, that means y is equal to 2. So the y values for which x equals 7 are going to be, and I can put this in numerical order, 2 and 5. 2 and 5. Now, let's find the slope of the tangent line, because they're going to want the tangent line at both of those 2 points, the equations of the tangent lines. So that means we take this equation and use implicit differentiation. So that y squared minus xy plus 10 equal to 0. We just do the implicit differentiation. And now going right in, like the derivative with respect to x of this right here, y squared minus xy plus 10. And then the derivative with respect to x of 0. Now the derivative of y squared will be 2y. But of course, we're taking the derivative of y. That means we need dy dx in this. Now minus. Now that x times y, we're taking the derivative of a product. We must use the product rule. And that's this. The first, which is your x, times the derivative of y. That's going to be 1. But of course, we need dy dx since we're taking the derivative of y, plus the second, which is your y, times the derivative of x, which is 1. And notice I'm putting this in parentheses here. The derivative of 10 is just going to be 0. Equaling to the derivative of 0 is 0. All right, now let's simplify this a bit. 2y dy dx, bring that down. Distribute the negative over what's in the parentheses. This will be minus x dy dx. Minus times y times 1 will be minus y. And that's equal to 0. Okay, now I'm going to move all the terms that don't have the dy dx over to the other side. These two terms will remain on the left side, but I need to move the minus y over to the other side by adding y to both sides. That would mean 2y dy dx minus x dy dx is equal to y. The left side, I'll factor out the dy dx. That will mean, in parentheses, I'll have 2y minus x is equal to y. Now I'm going to skip this step by putting 2y minus x on both sides, but you're going to have to know, well, I'll include it. Because you're going to have to know you have to divide both sides by 2y minus x in order to get dy dx by itself. And I will continue this way up here. So that means dy dx is equal to y divided by 2y minus x. Now we got to find the slope of the tangent line for these 2 points here, 7, 2 and 7, 5. Because we let x equal 7, that means your y value is going to be 2. and 5. So that means you got 2 points here. At the point, we're going to start with 7, 2. Let's find out what the slope of the tangent line is. And I'm using that notation M with the subscript TAN for the slope of the tangent line. Here, the y is 2, so it'll be 2 over 2 times y. Again, that's going to be 2 minus 7. This will be 2 over 2 times 2 will be 4. 4 minus 7, that's negative 3. So the slope of the tangent line is at the point 7, 2 will be negative 2, 3. Now we're going to use that slope along with that point in our point slope form, which is in this case y minus y1 is equal to the slope m times x minus x1. And excuse me for trying to scrunch all that in because I have very little space left. So here you're going to have y minus y1 will be 2, equaling to your slope m, negative 2/3, times x minus x1, which is 7. So here y minus 2 is equal to, distribute the negative 2/3 over the x minus 7. This will be negative 2/3 x minus negative times that minus will make that a plus. That's like 7 over 1. So 2/3 times 7 over 1 would be 14/3. And then you're going to add 2 to both sides. This you're going to have to use the calculator to do this. So y is equal to negative 2/3 x plus, now 2 plus 14/3. I'll do this in the calculator. So in this case here, I got, for this, 2 plus 14 divided by 3. Then hit your math key and then select number 1 for fraction. This will be 20 over 3. So at the point 7, 2, the equation of that tangent line would be y is equal to negative 2/3 x plus 20 over 3. That's at the point 7, 2. Now at the point 7, 5, we have a different slope of a tangent line. So using this right here, we're going to replace the the y this time with 5. So it'll be 5 over 2 times y again, that'll be 5, minus x is 7. The numerator will be 5. 2 times 5 will be 10. 10 minus 7 would be 3. So the slope of the tangent line would be 5/3. And then we're going to still use that point slope form, but this time our slope is going to be 5/3. The point would be 7, 5. So here, y minus y1 this time will be 5, equaling to the slope of 5/3 times x minus x1, which is 7. So I'm using this point slope form up here to find out what the equation of the line is of the tangent line at the point 7, 5. So I'll bring down y minus 5 equals 5/3 times x will be 5/3 x minus 5/3 times 7 over 1 would be 35 over 3. And then add 5 to both sides. So that means y is equal to 5/3 x. And let's see here, minus 35 over 3, or negative 35 over 3, plus 5. That's the math key. Number 1, be minus 20 over 3. So the equation of the tangent line at the point 7, 5 would be y equal 5/3 x minus 20 over 3. Okay. So that's how you will complete that problem. Okay, look at example 8. Find the equation of the tangent line to the graph of the equation, of the indicated equation at the point with a given value of x. In this case here, we got xy minus 3x minus 4 equal to 0 at the point, well, at x is equal to 2. Well, let's find out what y is when x is equal to 2. So we just substitute each and every x in this equation with 2. So this will be 2 times y minus 3 times x, which is 2, minus 4 equal to 0. So that x is being replaced with 2, so I have 2y. This x is being replaced with 2, so I have minus 3 times 2, then minus 4 is equal to 0. Well, 3 times 2 will be 6, so I have 2y minus 6 minus 4 equal to 0. Minus 6 and a minus 4 will be minus 10, so 2y minus 10 is equal to 0. Add sides. That means 2y is equal to 10. Divide by 2, you get y is equal to 5. So the point we're going to be dealing with would be the ordered pair 2, 5. And now we're going to use implicit differentiation to find the slope of the tangent line. So we got xy minus 3x minus 4 equal to 0. And we're going to differentiate each side of this equation with respect to x. All right, for the derivative of x times y, we must use the product rule. We have to use the product rule for this one. That means this, the first term will be x. The derivative of y will be 1, but we must include dy dx since we're taking the derivative of y, plus the second, which is your y, times the derivative of x, which is 1, minus the derivative of 3x. That would be 3. And then the derivative of a constant will be 0. And then equals to, the derivative of 0 is 0. Okay, now pretty much y times 1 will just be y. So I have x dy dx plus y minus 3 is equal to 0. And now I need to get the dy dx by itself. So I need to move the y over by subtracting y on both sides and adding 3 on both sides. So I'm moving all the terms that don't have dy dx over to the opposite side in one step. So I have x times dy dx is equal to, I'm going to write negative y plus 3 as 3 minus y. And then divide both sides by x in order to get dy dx by itself. That would mean dy dx is equal to 3 minus y, all divided by x. That's dy dx. So now, at the point 2, 5, where x is 2 and y is 5, I'll just substitute in here the y and the x and dy dx. So the slope of the tangent line, and by the way, this does represent the slope of the tangent line, by the way. So here we just substitute the x with 2, so it'll be 3 minus, actually substitute the y with 5, so it'll be 3 minus 5 over x, which is going to be substituted with 2. So in this case here, 3 minus 5 is negative 2. Divide that by 2, you'll get negative 1. So the slope of that tangent line will be negative 1 at the point 2, 5. Now let's look for the equation of that tangent line. Using, of course, y minus y1 is equal to m times the slope minus x1 times the slope times x minus x1. So here you're going to have y minus y1 in this case will be 5, equaling to the slope of negative 1 times x minus x1, which is 2. And if you need to be reminded, Your 2 is x1, y1 will be 5. All right. Distribute the -1 over the x minus 2. Bring down the y minus 5, and that's equal to -1 times x will be -x. -1 times y minus 2 will be plus 2. And then solve this equation for y by adding 5 on both sides. So that means y is equal to -x plus 7. So the equation of the tangent line to the graph of that indicated equation at the point 2,5 would be y equal -x plus 7. Okay. And finally, example 9. The demand, X, is the number of items that can be sold at a price of P dollars. Where X is equal to P squared minus 5P plus 200, we want to find the rate of change of P with respect to X by differentiating implicitly. So here we got an applications problem that we're going to solve using implicit differentiation. So we're finding the rate of change of P with respect to X. So in other words, the notation dP dx is what we're looking for, dP dx. All right, so here's our equation. X is equal to P squared minus 5P plus 200. So here we're taking the derivative of each term on both sides of this equation with respect to X. All right, the derivative with respect to X of X, that's obviously going to be 1. That's equal to the derivative with respect to X of P squared. We bring the exponent down of 2, copy the variable over to the 1 less power. But since P is some function of X, we have to include dP dx minus the derivative of 5P will be 5. Since P is a function of X, we'll have to say dP dx. The derivative of 200, like the derivative of a constant, is 0. Now, since I got dP dx on both sides, on this side right here, on the right side, I can go and factor out the dP dx. So I'm left with just 2P minus 5 in the parentheses. Now I can easily get dP dx by itself by dividing both sides by 2P minus 5. So that means dP dx then will be 1 over 2P minus 5. Okay. And that is what they are looking for in this case. So 1 over 2P minus 5 equaling to dP dx, that represents the rate of change of P with respect to X. Okay, and that's all they were looking for in that particular example. Okay, so that does conclude this video on section 3.5 dealing with implicit differentiation. Please feel free to reach out to me if you have any questions about any of the homework that's in my MATLAB or any questions about any of the problems that were presented in this video.